6.6 half-life homework. The first question says the mass of a sample of radioactive isotope is 64 grams and there's a count rate of 800 counts per minute. It is a gamma emitter, so it's got a half-life of 30 minutes here. So it's just showing you here the original amount, one half-life, amount remaining is halved, and then amount remaining is halved again, and then another half-life, amount remaining is halved, and so on. Find out how many half-lives it takes for the count rate to fall to 50 counts per minute. Well, if it starts at 800 counts per minute, we need to do the steps. So the step 1, we would write them out until we get to 50. So we take our largest value, and then we keep halving until we get to our smallest value. And then we just add arrows in between. And you can see there's 1, 2, 3, 4 half-lives. 4 half-lives, which takes us on to the next question there. How long does it take for the count rate to fall to 50 counts per minute? Well, it says here that it's 30 minutes. So we just times 4 by 30 there, and we get 120 minutes. That's the time, because you've got 4 half-lives, a half-life each worth 30 minutes. It says that there, says it there. What mass of the radioactive isotope remains at this time? So if we're looking at mass, we start with 64. Again, I've got it from this bit of the information, and then I'm going to go down here. So if it starts at 64, it's going to half, it's going to half, it's going to half, it's going to half. So we've essentially got 4 half-lives. 1, 2, 3, 4, which we've worked out previously, and it just wants to know after 4 half-lives how much is he going to have left. So the mass is just going to be 4 after 4 half-lives. So that's what I've put in there. Explain why this radioactive isotope would be suitable as a radioactive tracer in medicine. Well, because it's gamma, even though it's the most powerful, the most penetrating, it is the least ionizing. So does not ionize the cells as much as alpha or gamma. Alpha, as I explained in a previous video, has got a +2 charge because it's looking because it spits out 2 protons, 2 neutrons. Though that helium nucleus is essentially after 2 electrons, and then as much as gamma, I've made a mistake there. Look, that's what's throwing me. So that should have been beta, obviously. It does not ionize the cells as much as beta. Beta is 1 electron, so it's looking to pick up A positive. That's what ionizing means. Gamma isn't like that because it's a wave, so it's not that ionizing, which is safer in small amounts. It's still quite penetrating, and it's got a short half-life, so it's used as a tracer to track the journey of fluid. And I've said it's penetrating there, so it detects outside the body easily. The next one, there's a lot of reading in this question. So it says, living animals take in a small amount of radioactive carbon-14. After death, the amount of carbon in their bodies decrease because carbon-14 atoms decay. The amount of carbon-14 remaining in the bones of an animal skeleton can be used to estimate this age. So carbon-14 is a beta emitter, so it's beta decay. It's got a half-life of 5,720 years, which is quite a long half-life. State what is meant by the following statements. Carbon-14 is a beta emitter. Well, beta emission is just electrons, fast-moving electrons. Carbon-14 has a half-life of 5,720 years. Well, that is just the time taken for half the mass, really, or half the count rate, or half the number of nuclear atoms to fall by half. So it's just, in that time, this element, this carbon-14, is going to decay by half. And then complete the decay equation for carbon-14 shown below. Well, because we got the electron, this is always going to be 0 up top, -1, because electron is -1. Again, this side is, so let's draw that. So let's use me fancy thing. This side is always going to be equal to this side. So you can see here we've got 14 and 6. Well, 14 plus 0 is still equal 14. And then 7 plus minus 1 is going to give us 6 there. So you can always check to see if you're right. A bone taken from a skeleton found in the archaeological site contains carbon-14. Identical bone in a living animal. Oh, sorry, I missed that bit then. 10 units of carbon-14. An identical bone in a living animal contains 160 units. So use your understanding of half-life to calculate the age of the skeleton. So we need to get 160. We need to take this big value and get it to 10 by halving it every time. So you can see there 160, 80, 40, 20, 10. Arrows. There are 4 arrows. So that's 1, 2, 3, 4 half-lives. 4 times, and this is where students miss out on marks because they don't realize it's all part of the same question. There's your half-life, 5,720 years. So I'm just literally timesing 4 by 5,720. It's going to give me that age. Explain why this model of calculate the age of bones is unreliable for skeletons believed to be less than 100 years old. Well, because it's got such a long half-life, 100 years is just a fraction of that. So it's not going to really show much there. So I said 100 years is only a small fraction of the half-life. Difference in carbon-14 readings will be too small to even look at. Oh, you're going to love this one. Read the information in the box. I mean, that's where students fall down. Full stop. They just knock off because there's a lot of reading. But you've got 2 marks there. Now, 2 marks may not seem like a lot, but if 2 marks gets you to that C, then this is a lot. And it's just the sake of reading. Okay, even if you want to, as a tip, look at the question first. State how a picture of a path taken by a radioactive tracer is produced. So now you know what you're looking for. So when I'm reading this now, I know that I'm looking for something to do with gamma cameras. So I've got there, it says it has a half-life 6 hours, it only emits low energy rays, which easily escape the body and detected by a gamma ray camera. Okay, so using the information from here, I've been able to say that computer generated from readings picked up by gamma ray camera. And you can see that, there we are, builds a picture of the path taken. So all that, it's all there. So I wouldn't lie to you. And then give one reason why technetium-99 is a suitable material to use as a radioactive tracer. I said it's low energy gamma emitter and escapes the body easily. That's information I knew anyway, but if you didn't, it's got a small half-life, low energy gamma rays, okay? Escapes the body easily. So it's all there. 2 marks, just for reading. How lush. Then, the calculations. The patient was given the injection, part of which contained 1,280 undecayed atoms. So these haven't decayed. So this is the starting of the journey. How many of these atoms will have decayed after 6 hours? Well, from that information, 6 hours is 1 half-life. So it's just got 1 half-life. So I'm just halving it. Half of 1280 is 640. And I've done a little calculation there, just to help me pick up marks. How long will it take for only 80 undecayed atoms to remain in the patient? So again, I'm going to do my calculations. I'm going to keep half in half until I get to 80. Take my biggest value till I get to 80. 1, 2, 3, 4. There seems to be a theme in this paper of 4 half-lives. 4 times 6 hours, which I got from the question back up there, is going to give me 24 hours. Lovely. Might have to do this in 2 parts, so this will be the start of my next video. Homework 4 says, a radioactive substance which decays by gamma emission was placed in front of a detector. So there's my radioactive substance, here's my detector. Ooh, I like this because it's got a table, and I'm likely to gain 3 marks just for plotting my graph and drawing a decay curve. Easy marks, lush, that's what I like. So I've plotted them correctly. So if you look, I've put 0. Each small, so it's all about scaling here. Each small square is worth 10. So 480, then I come down to 290, then I come down to 180. So you've got to be very, very accurate when you're plotting and precise. And then that's for another mark, so we can gain 4 marks from this question alone. It says use a graph to find the half-life of the substance. Well, if we're starting at 480, half of 480, and I've done the calculation there, is going to be 240. So at 240, I just draw it across, and it comes just before that 7.5 mark. So I've said 7 there, but the mark scheme is going to say approximately 7. So if you say, I don't know, 6.5, anywhere from 6.5 to 8.5 maybe, you're going to get the mark. So easy marks. It's positive, it's all good. The table gives you information about some radioactive isotopes. So you've got just half-lives and which type of radiation it emits. Explain the meaning of the term half-life. I've said it's the time taken for the activity or the mass or the nucleus of the atom to reduce by half. And select the most suitable radioactive material for use in each of the following applications and give a clear answer for your selection. Now, for monitoring the thickness of aluminium sheet in the factory, this is a funny one, because when I looked at them, I was expecting to see, because if we know that beta can't go through aluminium, then I would be expecting gamma to go through that aluminium to be detected. Just like the paper mills use beta to detect the thickness of paper, because obviously paper blocks alpha decay, I would have thought gamma would be that one. But the mark scheme says it's strontium 90, and it says it needs to be beta because fewer particles pass through thicker aluminium and has a long. So the fact that it has a long half-life means it doesn't have to be replaced anytime soon. So companies are going to use a long half-life. Otherwise they're replacing it every couple of hours if they use a short half-life. But that threw me a little bit, I'll be honest. The strontium 90, and I'll probably check up on that, threw me. I mean, I'm sure it's right because it's in the mark scheme, but you would be forgiven to go for maybe a short half-life in gamma. I probably would have gone for technetium 99 there for 8 hours. Sorry, a long half-life. So I would have gone for cobalt. Cobalt 65 years needs to replace, and it's gamma. That's what I would have done, but we've gone for strontium, which is beta decay, of 29 years. So here we are. Learn something every day. Monitoring internal organs in the body. This one's slightly more easy because you're looking for a gamma. So if you're using anything in the body, you want it to be not ionizing. So gamma is less ionizing, and we're looking for a really short half-life. So to use cobalt 60, that's going to stay in your system for 5 years. We need something out of our system in 8 hours. We need something that's gamma. Let's use that one. We're going to use technetium 99. There we are, and that's that one done. And then it brings us on to the last one, which is another reedy question. Homeowner paid. Right, so the thing with this question, it's not relevant for us. So, I mean, this bit maybe, but we don't need to know about this bit. I noticed as I was doing it that we haven't got to factor in the danger factor, so we don't need to do that. But, yes, I think we just leave that one. So that's that paper. Done. Just scrap the last question.